Chapter 30, the Biot-Savart Law. Hans Christian Ørsted discovered in 1819 that an electric current in a wire produces a magnetic field nearby. It was found that the magnetic field lines formed concentric circles around the wire. So, if you took a compass, moved it around a current-carrying wire, you would find the needle would deflect in such a way as to indicate that there were circular lines of magnetic field around that wire. The direction of the field can be given by yet another form of the right-hand rule. If you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field around that wire. So in this case, the magnetic field is curling around this way as you're seeing it coming out of the page on this side, going into the page on this side, if the current were going up. Kind of like this diagram right here. Jean-Baptiste Biot and Félix Savart reported that a current-carrying conductor exerts a force on a magnet. Empirical observations led to the Biot-Savart law, which says that the magnetic field due to all wire elements ds that carry a current I exert a magnetic field a distance r away according to this nice expression here. Magnetic field is equal to some constant mu naught times the current I over 4 pi integration ds crossed with a unit vector r to the point divided by r squared, where r is the distance from the current carrying element to that particular point. This is a very intimidating formula. It was derived by both Biot and Savart separately, independently. They both were on the cutting edge of the science at the moment, and they both independently came up with the same law. We are going to look at this, but we're going to find easier ways to use this law. Note that mu naught is the magnetic permeability of free space. It is a universal constant, which you should memorize. Mu naught is 4 pi times 10 to the minus 7 Tesla meters per ampere. And you should memorize that. The permeability of free space. So, consider this. We're going to be looking at several wires, and we want to find easier forms of this Biot-Savart law. Consider having a wire with a current running along the x-axis here, and we're going to consider an element of that wire, ds. The magnitude of ds will be dx along this wire, and the magnitude of this unit vector pointing to the point here is going to be the magnitude of a unit vector, which is 1. So the magnitude of ds crossed with dr is going to be dx sine theta, where theta is the angle between the current direction and the vector pointing to that point as we move along this line. Bear with me. Let's express r and x and dx in terms of theta and r. So r, which is the hypotenuse of this right triangle here, is equal to big R, or capital R, which is the pure distance from point P to the line of action of this current, divided by sine theta. In other words, the hypotenuse times sine theta equals big R, which means that little r is equal to big R cosecant theta. X, by the same notion of the geometry here, is going to equal a negative r cotangent theta. So dx would be the derivative of this, which would be equal to r cosecant squared theta d theta. Like I said, bear with me. We're headed somewhere with this. We want to make these substitutions. So the infinitesimal field due to an infinitesimal piece of wire, ds, would be equal to mu naught I over 4 pi dx sine theta over r squared. Let's make our substitutions. And we have that the infinitesimal field at that point is mu naught I over 4 pi r cosecant squared theta sine theta d theta over r squared cosecant squared theta. One of the r's cancel out. The cosecant squared thetas cancel out. And if we now integrate from theta 1 to theta 2, being the lead angles, and taking out our constants, we have the magnetic field is equal to mu naught I over 4 pi r integration of just sine theta d theta from theta 1 to theta 2. Nice. An integral that we can do. Theta is our lead angle on one end and our lead angle on the other end. And the integration of sine theta would just be negative cosine theta, evaluate from theta 1 to theta 2, and that's going to give us cosine theta 1 minus cosine theta 2. So we have, for our final magnetic field at point P, a distance, pure distance r, away from the line of action of this current, is mu naught I over 4 pi r cosine theta 1 minus cosine theta 2. Theta 1 is the lead angle. It's the angle between the current direction and the vector pointing to the point on either end of this line segment. That's a nice result. It's one that we wanted to take note of. The direction of this magnetic field would be given by the right-hand rule. If I had a current going in positive x direction like this, if I point my thumb in that direction, the magnetic field will be coming around this like this, and at least on top of this wire, it's going to be coming out of the page towards you at that moment before it curls around. And underneath this wire, it's going to be actually going into the page. So at the point P, it is coming out of the page towards you. If the wire were infinitely long, then we could stretch x to negative infinity and to positive infinity. And if we were to do that, theta 1 is going to get smaller and smaller as we go to negative infinity. In fact, at some point, it's going to be equal to 0. And then theta 2, as we go to positive infinity, is going to expand more and more, and eventually will become 180 degrees or pi. So those limits are going to give us a theta 1 of 0 and a theta 2 of pi. Put that into our formula. Cosine of 0 is 1. Cosine of pi is a negative 1. So a 1 minus a negative 1, which would be 1 plus 1, or 2. And our magnetic field would then be mu naught I over 2 pi r. So the magnetic field, a distance r away from an infinitely long wire, is mu naught I over 2 pi r. That's a nice result. And again, pointing my thumb in the direction of the current, the magnetic field at point P in this case is coming out of the page towards you. Consider the magnetic field produced at point P if you have a section of wire and point P is off the end of that section of wire, say from A to B here. Well, if we apply our formula, in this case theta 1 is going to be 0, and from point B to point P is also, we're going to have an angle of 0 between the current direction and the vector pointing to point P. So we're going to have cosine of 0 minus cosine of 0, 1 minus 1, which is 0. So there is no magnetic field off the end of a straight current carrying wire segment. Magnetic field is indeed 0. What about a curved segment? Well, let's apply the Biot-Savart law to that. We're going to consider an arc of length s and an infinitesimal piece of that arc, ds, as we go through a curved segment of radius r. The infinitesimal amount of field that we have due to each ds on this is going to be equal to mu naught I over 4 pi ds over r squared. The magnitude of ds crossed with the unit vector to that point P is going to be equal to ds times 1 times the sine of 90 degrees, which is going to be ds. The direction of this magnetic field, if I were to use my right-hand rule pointing in the direction of the current, everything to the interior of this curvature is going to be into the page, away from you. Everything to the outside of this curvature would be out of the page, towards you. And point P is on the inside of that curvature, so we're going to have it away from you. You're looking at the tail feathers x as that magnetic field is going into the page. So let's integrate this over the arc length. We have mu naught I over 4 pi r squared. Constant's taken out of the integral because r actually is going to be a constant as we go through this curvature. It's not going to change, so we can take that out of the integral. And we have the integration from 0 to our arc length s ds, which is simply going to be just s. So that's mu naught I s over 4 pi r squared. S is the arc length, which is equal to the angle theta times the radius of the arc, if theta is in radians. So this is going to be equal to mu naught I theta over 4 pi r, where theta is measured in radians. That is the magnetic field at the center of an arc of radius r with angle theta in radians. How great is that? If theta were a half circle, then theta would be equal to pi radians. And this magnetic field at the center of that half circle would be equal to mu naught I over 4r. If we had a full circular loop, then the magnetic field would be equal to mu naught I over 4 pi r times 2 pi, and that would be mu naught I over 2r. And the direction again for that magnetic field would be into the page. We can use this form of the right-hand rule, but later on we're going to introduce another right-hand rule for circular loops, where if you curl your fingers in the direction of the current, in this case clockwise, your thumb points in the direction of the magnetic field due to that loop. So you can't go wrong. Either one works. Point in the direction of the current, fingers curl in the direction of the magnetic field into the page, or curl in the direction of the current, thumb points in the direction of the magnetic field into the page. So a summary: the magnetic field due to a straight wire segment is equal to mu naught I over 4 pi r cosine theta 1 minus cosine theta 2, where theta 1 is the lead angle between the current direction and the vector pointing to the point, and theta 2 is the lead angle between the current direction and the final vector pointing to the point. If the wire is infinitely long, this simplifies to mu naught I over 2 pi r. And if the point P is off the end of the segment, the magnetic field is 0 due to that segment. And finally, if we have a curved segment, the magnetic field at the center of curvature is equal to mu naught I over 4 pi r times theta in radians, where r is the radius of that curvature. You cannot use degrees here. You have to use radians if you use this formula. Most problems will be a superposition of these results. So rather than using that complicated Biot-Savart formula now, you can use these simplified results for various points of a problem. If I had a wire configuration that had straight segments and curved segments, what I would do is break them up into different portions, the straight segments and those curved segments, solve for the magnetic field due to all those sections, and then superimpose those results together at the end to get my final magnetic field at a particular point. These are techniques you should really learn to love, because if you go and take a electrodynamics course later on, they're going to show you much more complicated ways to work with the Biot-Savart law and come up with results. And in the back of your mind, you should remember that these are the simpler formulas that you can apply to find your results and know what the answer is, even if you're forced to do other ways to solve the problem. Know that you can still solve the problem using these techniques. So let's try out a problem. A conductor is in the shape of a square of edge length 0.4 meters, carries a current of 10 amps. Calculate the magnitude and direction of the magnetic field at the center of this square. Now if I'm looking at this, let's just look at one segment of the square, because that's what we want to do. Is we want to break it up, and we have 4 segments, but let's just look at one of them for the moment. Let's look at this down segment with the current going like this. If I were to apply the right-hand rule, with a current going down like this, everything to the left of that current is going to be into the page at point P. So it's going to be going into the page there. And if I look at the bottom segment with the current going this way, everything above it is going to be into the page at point P. And if I look at the segment with the current going up, everything to the right of that segment is going to be into the page. And for the current going across like this, everything below it's going to be into the page. So all four of these segments are going to be contributing to magnetic field that is going into the page away from you. And by symmetry, there's no reason why one segment would contribute more magnetic field than another. They're exactly in the same configuration. So at point P, the magnetic field is going to just be 4 times the magnetic field of just one of those segments. So if we can find the magnetic field due to one of these segments, we can find the magnetic field due to this full square configuration. Sounds good. So that's our objective. So the total magnetic field would be 4 times the magnetic field due to one segment, which would be 4 times mu naught I over 4 pi r cosine theta 1 minus cosine theta 2. Now you may know by looking at geometry here that theta 1 should be 45 degrees and theta 2 is 45 plus 90 or 135 degrees. Okay, so you can plug that in for your theta 1 and theta 2. Suppose you knew that theta 1 was indeed 45 degrees and that the cosine of theta 1 was the square root of 2 over 2. Well, suppose you didn't know what the cosine of 135 degrees was. Well, one thing that you can use on a lot of these problems is the fact that supplementary angles, in other words, angles that add up to 180 degrees, supplementary angles have negative cosines of one another. So in other words, in this particular case, theta 1 is actually a supplementary angle to theta 2 because this angle over here is also theta 1. And when they're supplementary, that means if the cosine of theta 1 is the square root of 2 over 2, the cosine of theta 2 is going to be a negative square root of 2 over 2. Supplementary angles have negative cosines of one another. And if I knew that, then that would make this calculation a whole lot easier. In other words, this is going to be 4 times mu naught, 4 pi times 10 to the minus 7 times 10 amps for the current over 4 pi. R is the pure perpendicular distance to the line of action of the current. Line of action of the current is going this way. R is this pure distance from point P perpendicular to that line of action. In this case, it's going to be half the distance of a side length. So that's going to be 0.2 meters. We have cosine 45 degrees minus cosine 135 degrees, which is going to be the square root of 2 over 2, minus a negative square root of 2 over 2, which is going to be the square root of 2 over 2 plus the square root of 2 over 2, which would be the square root of 2 over 2. So everything in the parentheses is going to be 1.414. And this will give us 2.83 times 10 to the minus 5 Tesla. So that is the magnetic field at the center of this loop. Its direction will be into the page, away from you. If this conductor is formed in a single circular turn and carries the same current, what is the value of the magnetic field at the center? So what we're going to do is take this square and we're going to bend it into a circle. We're not going to stretch it, we're just going to bend the wire into a circle. Hence the perimeter length of our configuration is going to remain the same. In other words, the perimeter of the circle, 2 pi r, has to equal 4 times L for the square. Based on that, we can figure out what the radius of our circle is going to be. It's going to be equal to 4L divided by 2 pi. 4 times 0.4 meters divided by 2 pi will give us a radius of 0.255 meters. Now we can calculate the magnetic field at the center of this circular loop because we have a result for arc lengths from the Biot-Savart law. So our magnetic field should be equal to mu naught I over 4 pi r times theta. In this case, theta is going to be 2 pi radians. So that's mu naught, 4 pi times 10 to the minus 7, times the current, 10 amps, over 4 pi times the radius of our curvature, 0.255 meters, times our angle in radians, 2 pi radians, and that gives us 2.46 times 10 to the minus 5 Tesla. Actually, slightly less than what it was when it was a square. The direction of this magnetic field, again, if I were to follow the current as it were going clockwise, the direction will be into the page on the interior of this loop. Or if I were to curl my fingers in the direction of the current clockwise, my thumb will point in the direction away from you into the page. Again, the magnetic field will be in that direction. This gives you the basic tools to solve configurations of current, either segments or curved segments, and find the magnetic field at a particular point. Try your hand at some of the problems in the problem set for the Biot-Savart law.